The talk I'm giving is kind of my view towards explainable AI. More than one of our sessions will be kind of talking about machine learning and microscopy. And so I thought this would be a good opportunity to talk about some of the issues with AI, why we might think about explainability. I have not put anything related to microscopy in this talk, so I'm hoping that for those of you who have that expertise, you could give me feedback and kind of we could discuss how these things fit in the microscopy world, either today or later in the program. So please do feel free to interrupt at any time. This will be a collection of joint work with these lovely folks here. So Dr. Han Liu, who's now at University of Wisconsin, Laura Balzano, who's been at University of Michigan, my PhD student Chris Stromier, Longju Wang, who's now at MSU, and Keenan Ham and Hongshin Tsai, who is also now at Central Florida. In addition to those people, a lot of the experiments that I'll get to at the very end are work from several REU programs. So these are pretty large REU groups. These are kind of morphed into one, and you can probably guess the years given the photographs. So thanks to all of those students for a lot of the applications. So this is just some motivation at the beginning. And again, this is not a microscopy focused motivation at all, but I hope that some of these, especially image processing applications, might kind of have some bearing in that world as well. So probably many folks have seen these, so I won't spend too much time on them, but I just kind of want to set the stage for what I'll talk about next. So this is kind of a famous example where a neural net is trying to classify an image. For example, this image here should be classified as being a panda. If we add some very small noise, and I say noise, it need not be random, right? It could be adversarially chosen, in this case especially, but it can be very small so that to the human eye, this still very much looks like a panda. However, with 99% confidence, the neural net now believes this is a gibbon. And I didn't actually know what a gibbon looked like, so I found one online. And so you see there's some similarities, but it clearly should not be mistaken for a different animal. Similarly, you see this is also kind of a famous one where a pig under the same sort of premise is misclassified as an airliner. Clearly the ears there maybe being the issue. But again, this is clearly a major problem in many applications. Besides adding things that look like noise, we have things like rotations can cause the same behavior. So this revolver image is just rotated and now it's confused with the mouse trap. The boathouse image is also rotated and now it's confused with the guillotine, and China cabinet becomes a spotlight and so on. And other imaging problems, for example, this is in facial recognition and facial detection. You can design glasses, and this is an example of one pair of glasses that were designed to not only become not a face, so you can just wear these and the facial detection algorithm will not even detect that you are there. Moreover, you can actually design the glasses to try to become somebody else. So if you have enough data on somebody else's face, you can actually design them to become that person. And so this is, a literal example of a reality in which, the Clark Kent Superman thing is actually real. And so this is quite staggering, I think. So moreover, a lot of this has to do with bias and how bias propagates through machine learning. And so this is some work that I'm interested in. I'd be kind of curious to see if this plays a role in any of the microscopy applications. But lots of examples where, a person of color might just stick a white face in front of their actual face, and that changes completely the way the algorithm recognizes them, computes their likelihood of getting a loan and all sorts of things, which are highly problematic for many, many social reasons. In self-driving cars, this is an issue, and so I would guess that in our applications, this would also become an issue. This example happens to be of a car trying to recognize a stop sign. So on the left here, you obviously want the car to be able to recognize a stop sign that is robust to things like graffiti and stickers and such like this. On the left, it does a fine job recognizing it as being a stop sign, but this rightmost picture where these stickers are sort of more strategically placed, it actually misclassifies this as being a speed limit 45 sign. clearly you can imagine a situation where a car thinking that the speed limit is now 45 rather than stopping would be highly problematic. So lots of concerns there. And by the way, I've cited all of these examples in the papers if you want to read more about them. So this goes outside of imaging. There are other data sources where we have this type of problem, of course. This is an audio processing example where we have a waveform that records the speech. It was the best of times, it was the worst of times. And again, you kind of add this seemingly noise. The waveform, to the human eye and to the human ear seems the same, but it's completely misrecognized now as something the text has completely changed. In transcription applications, there's also issues with accents. So this is a study that was done where they tested different accents, American, UK, European, Indian, and they also looked at the high SNR and the low SNR regime. And then they just computed the error rate, so how often a word was misread and misunderstood. And they did this with the human transcriber pool and the automated one. This is using the speech recognition software in this link down here. And so as you can see a couple of trends, right? One thing, the accents definitely matter. There's much higher misclassification rate, for example, Indian accents in both pools, the human and the model. This is likely due to the fact that the transcriber pool, even for the humans, was biased towards certain accents. And then kind of comparing the two, the model actually does much worse on some of them as well, especially in the noisy regime. More kind of NLP type of applications where we have a paragraph of text, this one talking about Peyton Manning and Super Bowl, and then we ping the model with a question. For example, what is the name of the quarterback who was 38 in Super Bowl 33? And the correct answer is John Elway, which if you just feed the model this block text, it can indeed give you that answer. But if you add just a little bit of extraneous information, which is factually correct, then you can fool the model, and the model will not give the wrong answer just by adding a simple sentence. Here's the famous kind of Pong example where the computer trying to play this game where it's trying to block the ball from leaving either side of the screen using these two automated paddles here on the left and the right. And so, for example, in this case, we have a very clean image. This is just doing it from a computer vision point of view. The ball is moving according to this vector. And so the correct movement for this paddle would be to move downward. So it would block the ball. If you just add, again, a very small amount of noise to the screen, again, to the human, it's hardly detectable. And now we've fooled the model to believing it should just keep the paddle where it is. So it should do no operation. You can also add very sparse noise and trick the model again for doing an incorrect operation. This I thought I'd just have in case we want to revisit it later. There's kind of this history of adversarial machine learning and security of deep neural nets. So there's a lot of crossover between the two worlds, and their timelines are a little bit different. Adversarial ML, according to this study, sort of started in the early 2000s, and security of DNN sort of picked up about a decade later. But there is a lot of crossover between the two, and I thought that was kind of interesting to see. So with all of this said, what do we do? So how do we protect against these kinds of adversarial attacks or biases that could look like adversarial attacks? From my perspective, there's sort of two main approaches. The first is to just keep training against adversaries. So you would generate adversarial data that fools your network, and then you would just train against that data. And so this does improve generalization, but it lacks robustness, as one might expect. For example, to me, it feels like this whack-a-mole game, which if you've never played it, it's a fun arcade game where you're smashing down little monsters that come up, and once you smash down one, another one just appears somewhere else. And so that kind of feels like this here, and it's not convincing that we would ever really get to a stable place where there wouldn't be any other possibilities. And the kind of other approach is defensive distillation. It's called a few things, which uses a second model, which is sort of smooth in adversarial directions, which really means it's trained on the primary model's output probabilities rather than the threshold of decisions. And the good news about this approach is it can be applied to any feed coral neural network. It reduced prior attacks, all the ones that were documented, from 95% to 0.5% success, meaning the attacks weren't successful. So it was much more robust against those attacks, but more recent work in 2017, for example, was able to actually construct some examples that fail even this approach. And so there's many of those benchmarks now. So still not really the answer. So you might kind of take a step back and say, okay, well, why do these models fail so easily? And I put easily in quotes, right? It's definitely not easy to construct those examples, but to the human eye, it seems like the model should do well, and it of course fails. So some thoughts, one would be that data is very sparse. The actual data that we see in practice is in a very large dimensional space, but itself is very small in that space. So there's lots of room to kind of nudge things around to get the model to make mistakes. Models are often very overconfident, especially given this little space that they actually have to go on. The amount of data that they've seen is incredibly small. And so I read this quote by Ian Goodfellow, the computer scientist, which I thought was pretty relevant. And he said that many of the most important problems still remain open, both in terms of theory and in terms of applications. We do not yet know whether defending against adversarial examples is a theoretically hopeless endeavor, or if an optimal strategy would give the defender the upper ground. On the applied side, no one has yet designed a truly powerful defense algorithm that can resist a wide variety of adversarial example attack outputs. So, given this, okay, how can we ever possibly trust an output, especially when we're doing something that we really do need to rely on the output? And so I'm going to kind of present a different approach, and it might kind of maybe spark some discussion and set the stage for some future work in our program. So these are things that I've been thinking about. If we could know why a model selects a particular output, not only do we understand the model better, so our human understanding, but we may be able to actually develop trust if we see over and over kind of the reasoning why a model does something that we want it to do versus we don't want it to do. And that would be, of course, a very cautious trust. And there are other approaches that do allow for this sort of transparency of understanding why. And so we're kind of I want to move away from the black box type of algorithms. Not to say that there isn't a lot of work going into understanding why neural nets do what they do and developing theoretical guarantees for them and so forth. And I think that's a great line of work. But I'm just going to take a little detour from that in this talk and talk about some other approaches, which will mostly be, will all be linear algebraic. So the first approach that I'll mention is non-negative matrix factorization. It's pretty widely used. I'll just give a brief overview of it. If we have a data matrix here, say the rows are users and the columns are variables, then the goal will be to factorize this into two low-rank factors. One is, say, a users by what I'll call topics, and then a topics by variables. And the sizes here are what we usually expect. It's usually a very small number of topics relative to the two other dimensions. So it's a very low-rank factorization. And as the name suggests, these two factors here will both have non-negative entries. So every single entry in both factors will be non-negative. And this is an example that sort of motivates, okay, well, why do we need non-negativity? Why is this actually important? And what does this have to do with this idea of explainability and interpretability in AI? So in NMF, each column of the data matrix must be represented by a non-negative linear combination of those dictionary atoms, which I'll call the first factor, the dictionary, and the second factor, the encoding matrix that explains how those atoms are used. And so in this example, or in this case, those dictionary atoms must be positive pieces of the data matrix itself. And so in this example, this is a famous example by Li and Sung, when each column of the data matrix, for example, is a human face. And so we see some examples over here on the left. Then what NMF learns are actually pieces of the human face, because they really need to add up in a non-negative way to construct a face. Then they end up being things that actually make sense to the human: a nose, a mouth, an eye. Those things can still be building blocks for the face, but they're actually meaningful to the human. Compared with something like PCA, for example, that still get building blocks for the face, but because you allow negativity, you get things that cancel out, and something like this doesn't really mean much to the human. It just happens to be something that constructs a face in a less meaningful way. And again, this was popularized in 1999 in this famous paper. Another way of kind of interpreting this, going away from images, we have a sense of how else one can use this idea of non-negativity, would be the following. So since everything is non-negative, large values have some sort of meaning for us, and small values would be less important. Again, in contrast to typical factorizations where those values don't necessarily mean anything about correlation or association. So in this case, I'm going to look for large values, and if I see a large value, say in this entry here in red, then that's going to tell me that this user corresponding to this row has a high association with whatever this topic is, which is going to correspond to this column. And so then I might say, okay, I want to understand what is this topic. This topic has been automatically identified as being important for the data. What does it actually mean? And so then I'll go into that corresponding topic and I'll look for its large values. And so say I see a large value here, it's going to tell me that this variable on this column must have a large association with whatever that topic is. And so I can now go between these two factors to really sort of understand what the topics have been represented. So just a kind of dive in for a concrete example, we could look at movie ratings, for example. So if the data matrix itself contains ratings where users have rated movies, then you can imagine maybe a topic is a genre or something like this. So I'd play the same game. I'd find a large value here and say, okay, this user has an association with this genre. They like this genre. They've rated that highly. And then I would go into that corresponding genre and I'd look at the movies that have large values. And then this is a little bit of a subjective interpretation, right? But maybe if the movies do have something in common that makes sense to me as a human, like in this case, they might be romantic movies. And so I can make that deduction. Again, in total contrast is something where I just see a bunch of positive and negative values. And to me, I have no way of really understanding what that means. So getting into kind of the more mathematics of the problem, the goal of NMF, again, is to factorize that data matrix X, which I'll say is now D by N, into these two low-rank non-negative factor matrices, which I'll call W, which will be the dictionary matrix, and H, which will be the coding matrix, and both of them will have rank R. So R columns in W and R rows in H. And what we're going to do is, the simplest thing to do would just be to minimize this Frobenius norm here. So we're literally just looking over all non-negative matrices W and H of the right dimension and find the ones that minimize the error in the Frobenius norm. And then we say that this is the approximation of the dictionary by coding matrix. And I won't go into details, but there's plenty of regularizers you can imagine adding. For example, L1 regularizer in both W and H that would promote sparsity, which again promotes more understanding. If there's less variables that have large values, then that's easier for the human to interpret what that topic would be. But there's many other regularizers that might make sense in different applications. I've also, I wanted to also mention an online version of NMF. Here we're looking for factorizations, but now the data is streaming in over time or being updated in some sort of way. And so we're looking to learn a factorization that is best, maybe an expectation if there's some randomness in the data stream. And we can actually, we developed an approach that allows us to use this online NMF for prediction, for example, in time series data. And I'll just quickly mention this, and then if I get to applications in the end, I'll kind of re-explain what I mean. But you can imagine, I'll show you this schematic again in a moment, but if X1 and X2 and X3 are the data points that are changing, so your data matrices that are changing over time, then you're constantly learning factors W and H, and those are changing over time. And I'll mention the iterative method to do this. But at any point in time, I can stop and I can multiply these two, and I can see whether it approximates X5, for example, in a good way. And so you can imagine kind of doing this with a sliding window. And I'm learning these factors as I go in this window. And if I kind of scoot that window off into the future where I don't actually have data, then instead of doing an approximation, I'm actually doing a prediction. And so I can use that to actually predict data into the future. And we have some applications in the end that shows the results for that. And I'll just briefly mention that everything I'm saying applies to tensors as well. So if your data is in tensor form, not a problem. All the methods that I'll explain can be extended to that setting as well. They're non-trivial extensions, but they do actually go through. Okay, so I'll just mention maybe a little bit algorithmically. Again, I know this is the first day, so we don't want to get in too deep, but at least it's here, and we can definitely go back over it as needed. But But typically, to actually try to minimize this Frobenius norm, for example, one uses something like Blockhorn descent, where you iteratively fix W and H and then minimize with respect to the error of the other. In a static case where X is not changing, then this is sort of the schematic that we end up getting, where W and H are changing just with this iteration. And if you actually use this model, you can develop a multiplicative update, which was first proposed by these two, again, back in their 1999 paper, which allows you to update all entries of H and W iteratively, just using a very simple update scheme. And you're essentially just computing gradients, and then the non-negativity actually comes for free. So you maintain non-negativity in this case. So it's a very simple iterative scheme. This is why many of the RU students can really jump in. So I think it's a good method to use. You get interpretability, you can apply it to many applications, and it's really easy for even the undergrads to jump into. So theoretically, it's not so easy. It is known that the error, this Frobenius error, is not increasing with this update scheme, but no guarantee to a stationary. So moving towards the online setting, now let's assume that the data matrix X is randomly drawn from some sample space according to some distribution pi. And then the question we have is, can we still learn the best dictionaries that describe X in probability or in expectation? And so this gives rise to the online NMF scheme, which goes back to the schematic I mentioned a second ago, where now your data points are changing, and then you'll have to update your iterations as the data changes as well. And in our case, ignore this text for the moment. And what we're going to hope for is we have some stochastic process, xt, and we're going to want to create factors W and H of the dimensions that we specify with rank R, so that the following convergence holds. So ideally, we would like this error at time t to converge to the best possible error, best meaning over the choice of W and H factors, where the error is taken with expectation over the distribution on X. So the best possible error in expected value. As I mentioned, you can add regularizers. And so for our exact case, we're going to actually use the L1 regularizer on H in this case, just to give us kind of a sparse encoding, which again allows you to interpret those topics a little bit better. For example, the movie case, if I had a bunch of large entries, a bunch of movies that had large entries, that'd be a little bit harder to suss out what's going on. So this is a very reasonable regularizer, and this will be the loss function that I'll consider. And then we'll define the expected loss in this way, again, taking over some distribution. We'll call it f of W, and then the empirical loss will be the average, the loss up to time t, and we'll call it ft of W. And these two terms will be important in the scheme. So there's a couple of things one can assume. So I'll mention a result that assumes independence on the data points, x1, x2, x3, and so on. We didn't really feel that independence was a very reasonable assumption in the applications that we were working in. For example, we were studying this in March 2020, and there happened to be some COVID data around back then. And so we were looking at trying to predict COVID cases. We also looked at weather data and other things like this. None of those really felt independent. At least one would hope that the number of cases on Tuesday would be dependent on the number of cases on Wednesday. And so we thought maybe at least taking it to a Markovian setting would be one step towards getting closer to reality. So we considered a Markovian assumption, and so we used some theory there to show that, for example, you get sort of for free that this empirical loss converges almost surely to the expected loss. And so one might say, okay, then all I have to do to make this update scheme an online version is just to update each H and T sort of given the empirical loss, for example. That's something that I actually have my hands on, and so I could optimize over that. A couple of issues with this. One is that it requires you to store all of the previous matrices, the WCHs, the X's for that matter, and also solve many optimization instances going between these two. So a little bit infeasible in practice. But this group of folks here gave a great solution to this problem, and they derived a method that actually overcame both of those, and they analyzed it in the independent case. So for IID data, they were able to actually prove some theory. And their scheme is to again try to solve this problem, but we made a little small change here. So instead of having this, instead of having the empirical loss here, we have a surrogate for the empirical loss, and we'll call that FT hat. That's a convex upper bounding surrogate, which is defined in this way here. So we're recycling some of the matrices found previously, and that's really the key here. So recycling the previous found H factors, we can use them as approximations to the subproblems, and so we don't have to keep solving new optimization problems over and over. And then the last question is, well, what about the history? Do we really need to store all of the history, even though we've reduced the number of optimization indices? And it turns out you can do something clever, but actually quite simple, which leads to this scheme here. And again, I know the pseudocode, and we won't maybe go over the details, but the takeaway of this is that you can get away with creating two aggregate matrices, AT and BT, that sort of do all you need in terms of storage. So just storing AT and BT alleviates the need to store the history of all X, H, and W. So that alleviates a huge amount of storage costs potentially. So this becomes a very practical method and becomes actually quite feasible in practice. And the good news is they were actually able to prove something for this case. So back in 2010, this group, using this scheme with these values, under the IAD assumption, proved that if your data is IAD with common distribution pi, and you're computing W and H using the scheme above, then you get the following guarantees. So you get that the empirical loss and the surrogate that we're using for the empirical loss converge to the same constant almost surely. It's a good indication that that surrogate's actually enough. You get as well that you do get the gradient converging to zero almost surely, which is of course what you would want. So again, we were looking at this and we really wanted to take it into a Markovian setting. And so what we are able to prove using the exact same method, so the method actually hasn't changed, just the assumptions on the data. So now instead of having to be independent, we allowed it to be an irreducible Markov chain with unique stationary distribution pi. And using the exact same method, we get the same guarantees. So we get that the empirical loss converges in expectation to the surrogate. We also get that it converges, they converge to the same constant almost surely. And we also get that same gradient vanishing almost surely as well. So same theoretical guarantees, a lot different analysis, but this takes, in my opinion, maybe a little bit of a step closer to being reality. So I hope this motivates a little bit that we can use a method like NMF that allows us the interpretability, which is it comes from the simple fact that we have non-negativity in both factors, and yet we can still be very rigorous. We can still get mathematical guarantees while also having that human explainability. The other factorization I want to mention, and I won't go into nearly as much detail with this one, but this is a CUR decomposition. So it's widely used in matrix applications, and what we did was take that to the tensor setting. So just a brief review of what it looks like in the matrix case. So if A is, say, a D by D matrix, you construct the CUR decomposition by taking K columns from A, so it actually comes from your data. You call that submatrix C. You take S rows of A and call that submatrix R. So I'm just color coding them here, blue and red. And you look at the intersection of those, the physical intersection of those, and you call that U. So that would end up being an S by K matrix, and here it's just like the purple entries. And then there's the next result that says if the rank of U and the rank of A are the same, then this construction actually does give you a decomposition for A. So A can actually be decomposed in this way. And this would be the CUR decomposition. The reason I think that this is relevant for the previous motivation is, again, I'm using a decomposition to break down the data and make it more simple to understand, and I'm doing it in a way that I think would be interpretable, right? If I understand what the data itself is, then I should understand what CU and R are, since they actually come from the data itself. There's no real abstraction going on here. There are lots of ways, and again, I won't go into too much detail, but there are many ways to actually find the CUR decomposition. There are deterministic sampling methods that I've listed here, and there are random sampling methods where you have to choose your probabilities in specific ways. Leverage scores and uniform, and there's a couple of options there. The complexity, just to compare the CUR complexity with, for example, SVD is quite favorable. So CUR looks something like R cubed compared with the D squared R, and the dependence on D in the CUR case is only logarithmic. And so kind of the conclusion is that the CUR procedure is easy to implement, computationally cheap, and allows you for a bit more explainability in the composition. And so the question that we wanted to ask was, can the matrix CUR decomposition be generalized to the tensor case? Many things right in their algebra just break down in the tensor case. And so to carry that over was not obvious. So some motivation would be to look at the higher order SVD decomposition of the tensor. So it has multilinear rank, say R1 through Rn. That's literally the rank of each unfolding. And then the tensor HOSVD decomposition looks like this, where we'll just kind of look at the schematic. We end up with a core tensor here, C, and then we have a bunch of matrices that allow you to take mode-wise multiplication to reconstruct the tensor. Not horribly important, but just used as motivation. This kind of gets broken down by a bunch of unfoldings. Again, maybe I'll kind of skip over this because the details aren't super important. Complexity is quite favorable. But this kind of leads right to some motivation, going from the matrix CUR to the tensor CUR. So remember, the A is decomposed in this manner here. And I mean, the matrix is a tensor, so the first thing one might do, right, is just to consider this as a two-mode tensor. And you can indeed write this as a mode 1 multiplication and mode 2 multiplication product with these matrices here. And so this kind of led us to walk down the following road. And this is a pretty dense theorem, so I'm not going to try to explain the details. In fact, I'm really just going to draw a picture and say that the takeaway is that there is a procedure for which you can actually construct a CUR decomposition for a tensor. But because there's more than two modes, there's a couple of ways you can do it. So we proposed two different ways. One is called the Chidori CUR, and I'll explain where that name comes from here. And under this composition, which I'll explain in the picture because I think that's easier than reading all of this notation, you do still get guarantees like ranks are the same. You get a decomposition with an n-fold multiplication. You get guarantees about the ranks of each unfolding and so forth. And the second one is a fiber CUR, and you get the same sort of guarantee. So that's why we motivate this as being a CUR decomposition, because it has that same sort of flavor. We're going to extract fibers in each mode, and we're going to use them to reconstruct the tensor, and we still have guarantees about the ranks. So with all of that heavy notation aside, I hate talking about tensors because this notation is just so cumbersome, but I hope that these drawings will kind of give a hint at what's going on. So in this case, we have a three-mode tensor, which is this black rectangular cube here. And this is a picture of the Chidori CUR decomposition. And to construct C1, and from this picture, we obtain C1 by taking this kind of red or pink subtensor here and unfolding it along the first mode. So literally just taking that tensor and making it into a matrix along the first mode. C2, we do the same thing with this green tensor, and C3, we do the same thing with the yellow tensor. And this dotted line here shows the core tensor, the core subtensor R. And so these components allow you to actually construct the tensor together. And my postdoc, Longju Wang, was giving this talk, and Dustin Nixon was in the audience, and he commented that this picture looked like a famous game called Chidori. And this is a picture of the game piece there. So that's where the name comes from. The other one is a fiber CUR, which is kind of more generic. It takes fibers that look like this. And in this case, the lines correspond to rows of C2, and the red in between here correspond to the rows of U2 in this case. And then this core subtensor R is denoted here. And unlike this case here where it's restricted, the core subtensor R was literally the intersection, so it kind of feels more like a traditional CUR. And in tensor case, you don't actually have to even have that, and you can still get a decomposition. So there need not be intersections there. So again, kind of high-level takeaway is that CUR decompositions can be very useful in applications. They allow interpretability because they actually are part of the data, and they do extend to the tensor case with a little bit of extra work. I won't spend maybe a whole lot of time on this, because I did promise I would end early. But I'll just say that we have some work on these decompositions being robust. So if you're familiar with robust PCA, where you've got an assumption where you have some sort of low rank component plus some sparse component, either in the tensor or the matrix case, then the goal will be to return just the low rank component or its decomposition. And so this kind of models a case where you might have very few, but possibly very large corruptions in your data, and you can still reconstruct that low rank structure. And so maybe I'll skip over all of this. The assumptions are very similar if you're familiar with robust PCA, where you have some assumption on incoherence and you have some assumption on sparsity of the noise. And we have a method that essentially uses pieces of our PCA, robust PCA, to do a robust CUR decomposition. And we have some theoretical guarantees for the method. The complexity, again, is much lower than that of robust PCA. So in my view, you gain computational advantage and you also gain this interpretability. So it's nice that we have the robustness there. And you can use this for many applications. This here is just reconstruction. You can see the runtime for CURs is much faster. And you can also use it for video surveillance, separating foreground and background, kind of the same things that you've seen maybe PCA used for. So for the remainder few minutes or so, I just wanted to kind of give an onslaught of applications. I'm hoping that maybe some of them will gel and have some relevance to the things that we'll talk about in this program. So the first application I've worked a long time on is in studying Lyme disease. So this is a partnership with LymeDisease.org, a nonprofit patient advocacy group for Lyme disease, and they've launched something called My Lyme Data, where they've administered a very large survey endeavor across the United States that has about 18,000 patients who are in the registry, and they have been diagnosed with Lyme disease, either acutely or chronically. Lyme disease is a vector-borne disease typically transmitted by an insect bite, spiders, ticks, things like this, or some sort of other blood-to-blood contact. It's a very strong mimicker of other diseases. So patients are often diagnosed with multiple sclerosis, ALS, Parkinson's, fibromyalgia, and other things. And if it's not treated immediately, it often becomes chronic. The CDC estimates 300,000 new diagnoses each year, and this is very well known to be a huge underestimate. This disease is poorly understood, it's poorly funded, poorly diagnosed, and poorly treated. And so the CEO of LymeDisease.org, who's very active in this area, said this is a perfect type of study for data-driven research. So she launched the data, and we partnered with her shortly after. And so we've been doing a lot of work on this data and presenting it to boards of physicians and so forth. And one of the things that we did was we took a portion of the data that just focused on symptomology. So patients were asked to rate their symptoms in various different types. And we just applied NMF, a couple of different versions of NMF. And this is just an example of what you could take away from this type of data. So I'll just kind of focus on this rightmost plot here. This was the most recent variation of NMF that we used. And I have just taken these symptoms that are listed here on the left, and we've applied NMF with just 5 topics, so a very sparse factorization. And the darker colors, the reds and the oranges, indicate large values. And so the large values are the things that are important. And then we've just grouped them to make it look a little bit easier to read. So for example, this first topic on the left really only has the associations with these first 4 symptoms: nerve pain, psychiatric, muscle aches, and heart-related symptoms, and so on and so forth. So when we presented this to the Board of Physicians and clinical researchers, they noticed a few things after we explained what we were showing to them that they found quite interesting. One of them was this middle topic here that is associated with memory loss, twitching, sleep impairment, and cognitive impairment. And this to them screams some neurologic manifestation. There's been some conjectures for a few years now that Lyme, because it comes with co-infections, it has many different strains, might present differently in different patients. So there's a cardiologic manifestation where you really have a lot of heart issues. There's a neurologic manifestation. There's a musculoskeletal manifestation, and so on. And this just seemed to scream to them that these patients might be presenting with a neurologic manifestation. So the fact that these clustered together so nicely kind of supports that theory. The other thing that they liked was that the bullseye rash really did not play a role in anything. This is kind of supporting the recent belief that, unlike what was previously thought about a decade ago, the bullseye rash is not actually that common. And so even if a patient comes in without the bullseye rash, they very much could still have Lyme. So lots of kind of pointers to do directions of study. And this is just on one very simple NMF analysis. This is just an example for image reconstruction. Here are the atoms that we learned, some examples. And so you see kind of some nice textures and brush strokes that really do kind of have a flavor of the original artist. And then this can be used for compression reconstruction in quite a successful way. Probably not the most important application to have explainability, but if there's a reason you want to do compression with explainable elements, then this could be an option. This one I really like. This is for image co-segmentation. We actually used online NMF to take a random walk through the image and sample patches of the image. And then we use this to do a supervised NMF where we actually have label information as well. And so if there's no neural net involved here, it's literally just NMF. And we're trying to just predict what the images contain. So for example, these images here contain cows, these contain dogs, cars, and bikes. And then what we did was we looked at the values in the encoding matrices, and we actually asked which pixels have the largest values corresponding to the label that was given. And so we've highlighted those here in these pictures here. So it might be hard to see because it's probably small, but in these cow images here, we're highlighting the actual cows, which is good news, right? We're hoping that we're predicting that that image has a cow because it actually does have a cow, which is not obvious, right? It could be that it learns to detect grass, and then the grass becomes the reason it gives the cow label, right? So we really wanted to have that interpretability and confidence that the model was doing what we thought. For dogs, it tends to be the face of the dog, which is not surprising. Cars, these are all different cars, if you look carefully. Tended to be wheels and headlights were pixels that became very important. Bicycles, kind of similar, the handlebars, the frame, the wheels, and so forth. And somebody mentioned when I gave this a talk previously that this actually, it wasn't the shadow in the image that was most important. It was actually the top part of the body, which I found very interesting. So I think there's some nice things going on here. It could be the symmetry or some sort of shape that's detecting. So again, we get very good accuracy, comparable to a neural net for image classification, but we gain this ability to kind of look inside and say, well, why is the model classifying things the way it is? Just very briefly, this is an example of doing the prediction that I mentioned, and we could also do this with imaging. So if there's any kind of microscopy application lying in the background that has some sort of changing dynamics. Here again, as I mentioned, we were predicting COVID case information. So we took time series of COVID cases for these 6 countries, which were the available ones at the beginning of 2020. And these are the atoms that we learned. So just little patterns here in each case. Not a whole lot of understanding gleaned just from looking at the atoms, although you do notice that the orange curve China tends to be kind of off on its own, which makes sense for early 2020. Otherwise, we can use this for prediction. As I said, we're reconstructing the matrix for the data points that we actually have. And then if we kind of slide our window into the future, we can do reconstruction into the future, which becomes the prediction. And so here we're just showing an example of our predicted confirmed cases. Prediction is in red, and the actual data is in blue. And so you see for most of the countries, we actually do really well. So these kind of localized patterns are good at predicting what the next week or 2 will look like. This was on a time scale of about a week. And so for Germany, US, Korea, all of these, we did very, very well. For China, you see that we actually did have kind of a bad point here. So the reported cases dropped for a point in time, and then they spiked. And for our method, because we believe that those patterns are going to be predictive for the future, we kind of started predicting these spikes, which actually did not occur. So what I'd like to do down the road is combine this kind of localized prediction with a more global model, like an SIR model. We also looked at EEG data. using online MF again. This was in the UC Irvine alcoholism data set. They had 64 electrodes on the brain, and you're trying to classify patients exhibiting alcoholism and patients without it. And here's kind of just the electrode behavior for each of the 64 electrodes, which is kind of just a bunch of rainbows, not too much to take away. But we found some actually really interesting observations. So with EEG data, the kind of most basic thing one might want to do is just look at how the nodes correlate with one another, who fires together and so forth. And so just doing a kind of very basic Pearson correlation on the raw data. So this is 64 nodes on the column and rows, and large kind of dark blue values are large correlations. And so you see there's definitely a couple of nodes here that are very correlated, and then there's some kind of other smaller patterns in the nodes. And so what we were curious in doing was learning the dictionary atoms for this data, and then running a Pearson correlation on those dictionary atoms to see how it compared to the original data. As you may know, EEG data, right, is very noisy. So we're going to probably talk about that over and over this program. And so we asked maybe if the dictionary atoms, those correlations maybe were denoised, and that's kind of what we anticipate. This might be what's going on here. So this is the Pearson correlation for the online NMF dictionary atoms. And it might be that this is a very cleaned up correlation pattern from the original. It's not exactly clear. So we're working with some people in the neuroscience department to try to understand this. Something that was even more striking was not only did we want the raw data to have correlations, we wanted to see how the gradients of the raw data correlated. So not only were they active together, were they increasing or decreasing together, the different nodes. And so we just did a Pearson correlation with the raw data and the gradient, and you pick up some much more interesting patterns here. So the blue is kind of much more dense. We did the same thing with online NMF using the raw data and the gradient, and we get almost the exact same structure here, which tells you that the dictionary items are explaining the data in a good way. But this was a really interesting one, I think, which here we did not actually use the gradient. We just used the raw data. We learned the dictionary atoms using NMF, but we increased the rank to a bit higher. So we increased it by about double to 16. And now, even though we never fed it the gradient, this model did not see the gradient at all directly, it still seemed to pick up very, very similar patterns. And so this is really intriguing. We might be kind of stumbling upon something that says NMF somehow learns relevant information without you even needing to know what that relevant information is, right? So if I knew that the gradient was important, I could, give the gradient as input. But if I didn't know that the gradient was important, then I could still use NMF, and I could still sort of detect these interesting patterns and correlations. So this is something that's ongoing work, and I think really shows the power of what these methods can do. Similar example here in a mouse brain, studying active regions of the brain when a stimulus is being applied, and the dictionary atoms are shown here. If somebody who knows something about how the brain works might come in and say, oh, these areas of the brain are very interesting, when were they stimulated? Then you can go into the corresponding encoding factor and look at which point in time that region was active, rather than having to really go frame by frame and trying to piece everything together. You sort of learn the patterns from a very high level. So an interesting pattern there. Skip over that. This is the video surveillance where we're separating background and foreground. So these are the objects that are moving, and these are the static objects. And so we use, as I mentioned, a robust CUR, which is computationally advantageous as well compared to some others. Also used robust CUR to remove facial objects, saturations, and shadows, and things like this, similar to PCA. And I will pause there. I finished a little bit early, and if there's any questions, I am definitely happy to take them.